I'm Purujit, and today I'm going to present on a paper that describes two improvements to the Linux ext3 journaling file system. The paper is titled Wasteless Journaling for Fast and Reliable Multi-Stream Storage. The authors of this paper are from Greece. I don't want to butcher their names, so their names are right there on the slide. In this presentation, I'm first going to briefly introduce journaling in the context of file systems. Then I'm going to talk about the motivation behind this work and the design for a wasteless approach that the authors are proposing. Then I'm going to present some graphs that show the improvements from this approach. I'm going to conclude by summarizing related work and the technical contribution of this paper. Journaling is a well-known technique in database world where it's widely used to provide atomicity and consistency for transactions. The basic idea is that all updates first go to a journal, which is usually a sequential durable storage device. Since it's sequential, it can provide very inexpensive writes. Only after the journal is written, the main storage is updated. This approach provides atomicity and consistency because by the time the main storage is being updated, we have all the information needed to reapply the update, even if the first attempt fails. In the context of file systems, journaling is employed to keep file system metadata consistent. Sometimes it's also used for data. A good use case that illustrates journaling would be a rename operation. When we rename a file from one directory to another, we want the entire operation to either go through or fail totally without leaving any state behind. ext2 file system tried to achieve this in a failure recovery mode, where it walked the entire directory tree and tried to bring it to a consistent state. On a large volume, it used to take hours. ext3 was introduced in the late 90s to address this situation through journaling. As a result, ext3 recovery only takes minutes, since it only has to check the few recent entries in the journal since the last time the journal was checkpointed. The ext3 file system can operate in three modes: ordered, write-back, and data journal. They only differ the way they handle data updates, because all three of them handle metadata update by journaling it. In the write-back mode, data is not journaled at all, and there are no guarantees about the consistency of data. In the ordered mode, the data is first written to the file system, and only then the metadata is written to the journal. This makes sure that in the append-only mode, the metadata stays consistent. In the data journaling mode, both data and the metadata are first written to the journal and later asynchronously written to the main storage. This offers the best consistency at the cost of having to write the data twice, first to the journal and later to the main storage. But data journal offers another advantage in the sense that it has lower latency than the ordered mode, since data writes does not have to stall metadata writes. The authors have observed that for common write patterns in distributed environments, ext3 has some big inefficiencies. Such systems do a lot of order preserving data writes. For example, they need to do checkpointing or transactions, etc. These writes are small and usually issued as synchronous writes to the file system. Being able to serve this payload efficiently with low bandwidth usage and low latency is therefore important. On ext3 file system, however, even a write that modifies a few bytes of a page will cause the entire page to be written to the journal. This graph demonstrates the problem well. The blue line here represents data journaling mode in ext3 file system, and the red line represents ordered mode. As you can see, for small request size, the blue line stays high, indicating high journal volume. And this is because even for small writes, we are writing entire pages to the journal. Contrast this with the red line, which stays low for small request sizes because no data is being written to the journal. Based on this observation, the authors set the following goals for improved design. They want to reduce disk bandwidth waste. They want to keep small synchronous writes cheap as they are in the data journaling mode. And they want to maintain the same reliability and consistency as ext3 journaling modes. So their design approach basically centers around creating an abstraction that can hold multiple subpage updates in a single journal block. And that enables them to journal data updates at subpage granularity. Their design is apparent from this graphic. Here we have 3 modified data blocks. 2 of them are small and 1 of them is page size. When they're being written to the journal, they're being coalesced into 2 journal blocks, and therefore the journal write is smaller. Contrast this with ext3 data journaling, where each of the 2 subpage modified regions would have generated 2 full pages being written to the journal, as opposed to the 1 under the design. This approach is still wasteful for large writes because data is being written twice, first to the journal and then to the file system. They propose to improve on it further by another journaling mode they're calling selective journaling. The basic idea is that they want to transfer requests that are larger than a page size to the final location on the file system without making it to the journal. And they want to treat small requests according to the wasteless journaling, which we just saw. They are evaluating their proposed journaling modes in terms of latency, disk traffic, and they also ran some application workload benchmarks on their journaling modes. Here are the graphs for latency. In these graphs, they're comparing their 2 proposed journaling modes with ordered and data journaling modes of ext3 and a log-structured file system implementation on Linux. As you can see, on the read latency side, all the 4 modes perform equally well, and the log-structured file system is understandably much higher latency. The write latency is more interesting. As you can see, data and wasteless journaling achieves substantially lower write latency. And their write latency is similar to NILFS, which is the log-structured file system, which is good because the log-structured file system is known for having very low write latency. Selective and ordered mode gets high write latency because they both have to wait for data writes to complete before they can write metadata to the journal. Here, selective journaling behaves similarly to ordered journaling because we are issuing large writes. As you can see, they're using 1 Mbps streams. For writes that are smaller than a page size, selective journaling would behave similar to wasteless and data journaling. On the disk traffic front, on the left we have journal throughput, and on the right we have file system throughput. As you can see, on the journal throughput side, data journaling uses the most and ordered journaling uses the least, and wasteless and selective falls kind of in between because they try to coalesce journal entries, and in the case of wasteless journaling, it doesn't always write data to the journal. It only writes data to the journal if it's smaller than the page size. On the file system throughput size, ordered journaling has the most bandwidth usage since it writes every data update to the file system, whereas the others have much lower because they can coalesce subsequent writes to the same location with just one update to the file system. Therefore, we can see wasteless and selective journaling can substantially reduce both journal and file system traffic compared to the default modes that come with ext3. On application level workloads, their proposed modes perform very well. Wasteless journaling improves both transactions per second on the postmark benchmark and throughput in terms of megabytes per second on the parallel I/O workload. There have been some related work in this area. As I mentioned, log-structured file systems try to address the problem of duplicate writes to both the journal and the file system. They basically employ the idea of using the logs as the file system. There is no separate data. Log-structured file systems can offer fast writes, but are usually slow to read because you have to read sequential logs to find the data location. In the database world, there is also the concept of group commit, which try to coalesce multiple commits if they affect the same rows. There are also proprietary implementations by IBM and Microsoft, respectively, that support subpage journaling. These file systems are JFS by IBM and NTFS by Microsoft. To summarize, this paper proposes approaches for wasteless and selective journaling. Wasteless journaling merges subpage writes into page-sized journal blocks, and selective journaling only journals data updates that are smaller than the page size. These approaches provide performance benefits over ext3 by reducing write latency, improving transaction throughput, and avoiding bandwidth waste. Thank you.